Hello students, welcome to Diksha Karnataka YouTube channel. In this video, I am going to discuss top 30 questions in electrostatic potential and capacitance. Okay, so this is very important chapter for KCET 2024. Okay, so if you analyze the previous year papers, at least you will get to see at least they asked at least 3 to 4 questions from this chapter. Okay, so this is very important topic, and if you are able to solve these 30 questions, okay, so they will ask these kind of questions only. So if you are able to solve these 30 questions, then you will be able to solve, or you will be able to counter these kind of questions in KCET. Okay, yeah, let's start. Question number 1. A uniform electric field E vector exits along horizontal direction as shown. The electrostatic potential at A is VA. At this point, electrostatic potential is VA. A small point charge Q is slowly taken from A to B. Along the curved path as shown, the potential energy of the the potential energy of the charge when it is at point B. Okay, we need to find the potential energy of the charge when it is at point B, right? Okay, so first let us find potential at point B. Okay, then potential energy of the charge when it is at point B is equal to Q into VB, right? Q into VB. That's it, right? Okay, so let us find VB. So how to find VB, right? So we know the relationship between electrostatic potential and electric field, right? So the relationship between electrostatic potential and electric field is VA minus VB, difference in electric field, okay, potential difference, difference in electrostatic potential, okay, or potential difference equal to here E into X, right? So VB equal to VA minus EX, right? Now substitute here. So UB, that is electrostatic potential energy at point B, is equal to Q into VA minus EX. VA minus EX. So the correct option is D. Okay. Yeah. Next question. Question number 2. A parallel plate capacitor of capacitance C1 with dielectric slab in between its plates is connected to a battery. It has potential difference V1 across its plates. When the dielectric potential, when the dielectric potential difference are C2 and V2 respectively, then, okay, so here this is the parallel plate capacitor and dielectric is inserted in this parallel plate capacitor. It is C1, right? The potential difference is V1. Potential difference is V1. Okay. So now the dielectric is removed. Okay. Dielectric is removed, right? So what is the potential difference? Potential difference would be same, right? V2 is equal to V1, right? Potential difference would be same. Why? Because the same cell is connected, right? It is still connected, isn't it? But the capacitance changes, right? Here the capacitance is C2, okay, it is R, right? Here the capacitance is C2, right? Isn't it? When you remove the dielectric, then when the capacitor here, question number 2. A parallel plate capacitor of capacitance C1 with dielectric slab in between its plates is connected to a battery. It has potential difference V1 across its plates when the dielectric potential difference are C2, V2 respectively, then, okay, here when dielectric is inserted, the capacitance is C1, okay, the potential difference is V1. Here this will also be V. So V equal to V1, right? When you remove the dielectric, the capacitance is C2, right? Here it is just air. So what is the potential difference? The potential difference is V2, right? but the same cell is connected, right? So potential difference V2 is equal to V, right? So the potential difference does not change, right? V1 equal to V2. So what happens to the capacitance? The capacitance will be decreases, right? When you remove the dielectric from the capacitor, parallel plate capacitor, the capacitance decreases. So C2 is lesser than C1. Okay, C2 is lesser than C1. So option C is the correct answer, right? V1 equal to V2, C2 is lesser than C1. Yeah, next question, question number 3. 5 capacitors each of value 1 microfarad, okay, 1 microfarad are connected as shown in the figure. The equivalent capacitance between A and B. Here we need to find equivalent capacitance between A and B. Just observe the given diagram. Closely observe this given diagram. Okay, so this looks like the Wheatstone bridge, right? Balanced Wheatstone bridge. Now take the ratio here. 1 divided by 1 is 1. 1 by 1 is 1, right? So this is balanced Wheatstone bridge, right? So I can redraw this diagram as here 1 microfarad, okay, and then 1 microfarad, right? Here we can neglect this 1 microfarad capacitor, right? Because the potential difference will be 0. So there is potential at this point and this point is same. So potential difference will be 0. So there is no current or there is no charge flows through this branch or arm, right? So now these two are in series, right? Now what is the capacitance of these two? Here this will be 1 by 2 microfarad, right? 1 by C1 plus 1 by C2. C1 and C2 are 1 microfarad. So 1 by 1 plus 1 by 1, right? Isn't it? So 2 microfarad, 1 by C equivalent equal to 2 microfarad. So C is 1 by 2 microfarad. Same thing for this also, right? 1 by 2 microfarad. Now these two are in parallel, right? So this is C1, here this is C2. So C net is equal to C1 plus C2. So 1 by 2 plus 1 by 2 is 1. So C net equal to 1 microfarad. So the correct option is A. Okay. Next question, question number 4. The electric field and the potential of an electric dipole along its axis vary with distance r respectively. Okay. So this is the dipole, minus q and plus q. Okay. A, the distance between plus q and minus q. This is the direction of the dipole, right? The point P lying on the axis of this dipole. Okay. So here this is r. From the center of the dipole to point P, the distance is r, right? So electric field at point P is 2 kp divided by r cube, right? Here I am considering r is much greater than A. Okay, so 2 kp by r cube. So electric field at point P is directly proportional to 1 by r cube, right? Or inversely proportional to r cube, right? And the potential at point P is kp divided by, here kp divided by r square, right? Kp divided by r square. What is the potential at point P due to q? So it will be kp by r minus a, right? So this is 2a, kp by r minus a, sorry, here potential at point P is k into q divided by r minus a. Potential at point P due to minus q is k into q divided by r plus a. Solve this, you will get kp by r square, right? So potential at point P is inversely proportional to r square. So the correct option is C. Okay, 1 by r cube and 1 by r square, not A. Okay, they are asking just electric field and then potential, okay, due to dipole. So 1 by r cube and 1 by r square. Question number 5. Two tiny spheres carrying charges 1.8 microcoulomb, 2.8 microcoulomb are located at 40 centimeter apart. Here the sphere A, the charge on the sphere is 1.8 microcoulomb, and this is sphere B. The charge on the sphere B is 2.8 microcoulomb. It is separated by a distance 40 centimeter apart. Okay, the potential at the midpoint of the line joining the two charges is here. This is the midpoint. Okay, so what is the potential at the midpoint line joining the two charges, right? So what is the distance between sphere A and midpoint and sphere B and midpoint? It is 20 centimeter, right? Now potential at midpoint due to A, okay, which is equal to K Q divided by KQA divided by RA, right? QA is 1.8 microcoulomb, RA is 20 centimeter. So VA is equal to here K into 1.8 microcoulomb divided by RA, that is 20 centimeter. Okay, and then VB is equal to K into 2.8 divided by 2.8 microcoulomb divided by 20 centimeter. Okay, now potential at the midpoint is equal to VA plus VB. Okay, take K divided by 2 into 10 to the power 20 into 10 to the power minus 2 as common. Okay, then 1.8 microcoulomb plus 2.8 microcoulomb. So 2 plus 1 is 3, 0.8 plus 0.8, 1.6. So this will be 4.6. So 4.6 microcoulomb, that is 10 to the power minus 6 coulomb, right? Now V is equal to, what is the value of K? K is 9 into 10 to the power 9 divided by here 0.2 into 4.6 into 10 to the power minus 6. Now solve this, you will get V equal to 2.1 into 10 to the power 5 volt. Okay, so the correct option is D. Understood? Yeah. Next question. Question number 6. A parallel plate capacitor is charged by connecting a 2-volt battery across it. It is then disconnected from the battery and a glass slab is introduced between the plates. Which of the following pairs of quantities decrease? Okay, so this is the parallel plate capacitor. Okay, now it is charged by applying the potential difference 2 volt, right? 2 volt. Now the cell is disconnected, right? Cell is disconnected and glass slab introduced, right? The glass slab is introduced. So now what happens, right? Okay, so when you introduce the glass slab, definitely the capacitance will change, right? Capacitance will change. So what is the expression of energy? The expression of energy, Q equal to half into the charge Q into V, right? The charge Q into V. What is Q? Q equal to C into V. So it is C into V square, right? The charge Q into V. When you introduce the dielectric, so what happens? The potential, there will be a potential difference, right? Isn't it? There will be a potential difference, right? There will be a change in potential difference, right? Change in potential difference when you introduce the dielectric, right? So U, energy will change, energy stored will change, and the potential difference will also change, right? V will also change, isn't it? So the correct option is D. Okay, potential difference and energy stored. Yeah, next question. Question number 7. If a slab insulating material 4 into 10 to the power minus 3 meter thick is introduced between the plates of a parallel plate capacitor, the separation between the plates has to be increased by 3 into 10 to the power minus 3 meter to restore the capacity to original value. The dielectric constant of the material will be. Okay, we know that here the separation x equal to, okay, the increased separation x equal to T minus T by K. Okay, so if you don't know how we got this formula, go through the derivation. Okay, in NCERT it is there, x equal to T minus T by K, right? So x equal to, what is the value of T? T is 4 into 10 to the power minus 3, right? 4 into 10 to the power minus 3. What is the value of x? X is 3.5 into 10 to the power minus 3. So 3.5 into 10 to the power minus 3 equal to T. T is 4 into 10 to the power minus 3 into 1 minus 1 by k, right. Now what is the value of 3.5, right? We can write 3.5 in fraction, right, isn't it? So we can write 3.5 in fraction, so it is 7 by 2. So 7 divided by 2 into 10 to the power minus 3 equal to 4 into 10 to the power minus 3 into 1 minus 1 by k, right? Now 10 to the power minus 3, 10 to the power minus 3 will get cancelled, right? So this will be 7 by 8. 7 by 8 equal to 1 minus 1 by k, right? So 1 minus 7 by 8 equal to 1 by k, right? So this will be 1 by 8, right? So k equal to 8. K equal to 8. So the correct option is B. Okay, correct option is B. Next question, question number 8. 8 drops of mercury of equal radii combine to form big drop. Okay, 8 drop of mercury combine to form big drop. Let's say r is the small r is the radius of the mercury drop, small mercury drop. Okay, capital R is the radius of the bigger mercury drop. Okay, the capacitance of the bigger drop as comparable or compared to each smaller drop is. Okay, we need to compare the capacitance of the bigger drop with the capacitance of the smaller drop. Okay, so capacitance of the smaller drop Cs is equal to 4 pi epsilon naught into R, right? So this is the expression for capacitance of the spherical capacitor. Okay, here the mercury drop acts as a spherical capacitor, right? So Cs equal to 4 pi epsilon naught into R, that is capacitance of the small mercury drop. Now capacitance of the bigger mercury drop is equal to 4 pi epsilon naught R, right? Now we need to find the value of small r, right? I mean, we need to find the expression of small r in terms of bigger r, right? The volume of the 8 drops is equal to volume of the bigger drop because all the 8 drops combines or coalesce to form bigger drop, right? So volume of the bigger drop, that is 4 by 3 pi r cube, 4 by 3 pi r cube is equal to volume of the 8 drops, 8 into 4 by 3 pi small r cube, right? So capital R is equal to 2r. Solve this, you will get capital R equal to 2r, right? Now divide this Cs by, divide Cb by Cs. Now Cb divided by Cs is equal to 4 pi epsilon naught capital R. Okay, 4 pi epsilon naught capital R divided by 4 pi epsilon naught small r, right? Small r is equal to r by 2, right? Small r is equal to r divided by 2. Now Cb by Cs is equal to 4 pi epsilon naught will get cancelled, r divided by r by 2. Now Cb equal to 2 times Cs. Okay, now the capacitance of the bigger drop, if you compare the capacitance of the bigger drop with the smaller drop, then Cb is equal to 2 times Cs, that is capacitance of the bigger drop is equal to 2 times capacitance of the smaller drop. So the correct option is A. Okay, yeah. Next question, question number 9. An electrician requires a capacitance of 6 microfarad in a circuit across a potential difference of 1.5 kilovolt. Okay, that is 1.5 into 10 to the power 3 volt. A large number of 2 microfarad capacitors, which this is microfarad, okay, which can withstand a potential difference of not more than 500 volt, are available. The minimum number of capacitors required for the purpose is, okay, so he has large number of 2 microfarad capacitor and it can withstand 500 volt potential difference, right? But he requires the capacitance of 6 microfarad and it can withstand 1.5 kilovolt. Okay, so now he needs to combine or he needs to join 2 microfarad capacitors and forms 6 microfarad capacitor and potential difference 1.5 kilovolt, right? Okay, so he can join like this, right? This way, isn't it? This is the combination, right? So M is the number of capacitance in a row, okay, in this row, every row, okay, and N is the number of rows, okay, number of rows. Now here let us find the number of capacitors in one row, okay, number of capacitors in one row. So how to find? Here he has 2 microfarad capacitor, right, and it can withstand 500 volt, right? So the total volt is equal to here the 500 volt into M, right? 500 volt into M. So what is the value of total voltage? The value of total voltage is 1.5 kilovolt, right? That is 1.5 into 10 to the power 3, which is equal to 500 into M, right? So M is equal to 1500 divided by 500. So this will be 3. So M equal to 3. That is, in this row, total 3 capacitors are there, right? Okay, I will redraw this diagram. Okay, total 3 capacitors are there. Right? 3 capacitors are there. So what is the capacitance of each capacitor? 2 microfarad, right? 2 microfarad, 2 microfarad and 2 microfarad, right? So now what is the net capacitance? Here net capacitance is 1 by 2, 1 by 2, 1 by 2, that is 3 by 2, right? So 3 by 2 is 2 by 3 microfarad, right? So net capacitance is equal to 2 by 3 microfarad, isn't it? Net capacitance is 2 by 3 microfarad. Okay, so now here there are n number of rows, right? So we need 6 microfarad capacitor, right? Now C net dash is equal to number of rows into this net capacitance, right? 2 by 3, 2 by 3 microfarad, right? Now C net is 6, right? 6 equal to n into 2 by 3 microfarad, right? So 2 3s are 6, so n equal to 9, okay, n equal to 9. Microfarad will also get cancelled, so n equal to 9. So that is there are 9 number of rows, right? There are 9 rows, 9 rows, okay. There are 9 rows, isn't it? Now we need to find how many capacitors are there. 9 rows, right? In each rows there are 3 capacitors, right? So the total capacitors, okay, T equal to 9 into 3, so which is equal to 27. So he needs 27 capacitors, okay, capacitors of capacitance 2 microfarad, okay, to get 6 microfarad capacitor, and it can withstand 1.5 kilovolt. So option D is the correct answer. Next question, question number 10. In figure, charge on the capacitor is plotted against potential difference across the capacitor. The capacitance and energy stored in the capacitor are respectively. Direct question, right? How to solve this one? So here the charge and potential graph is given, right? Here this one is linear, right? So we know that the capacitance C equal to Q divided by V, right? So C equal to, the value of Q is 120 microcoulomb divided by voltage is 10. So C equal to 12 microfarad. Voltage is 10 volt. So C equal to 12 microfarad. So option D, C and D are eliminated, right? So let us find the energy. Here energy stored in the capacitor is half C into V square, right? Half C into V square, isn't it? Okay, but the capacitance, okay, we got the value of capacitance, right? You can use the capacitance value and voltage value, okay, you will get, or you can find the energy value by using graphs also, right? How to find? Take the area of this graph, right? So what is the area? Area will be u equal to half into height is q into base v. So u equal to half into q is 120 microcoulomb, right? 120 into 10 to the power minus 6 into v is 10. So this will be 60, right? So u equal to your 600 microjoule. So the correct option is B. Okay, correct option is B. Next question, question number 11. The figure gives electric potential V as a function of distance through 4 regions on x-axis. Which of the following is true for the magnitude of electric field E in this region? In this region, okay. Potential versus x graph is given, right? So we need to find electric field E in this region. We know the relationship between electric field and potential, right? So what is the relationship between electric field and potential? Electric field E equal to minus dV by dx, that is potential difference by dx, right? Okay. So here, if we take the slope of this graph, we will get the potential, right? Okay. In region A, the electric field is 0. Why? Because potential is constant. So constant of differentiation of constant is 0, right? So electric field at A is 0, right? So let us find electric field at B. Electric field at B, EB is equal to minus of dV, that is change in potential. So what is the change in potential? Here the change in potential is 2 volt, right? 2 volt, 4 minus 2. So 4 minus 2 divided by 1, right? 2 minus 1, 1. So EB is equal to minus 2 volt per meter. Okay, minus 2 volt per meter. Then EC, okay. At this region, here potential is, electric field is 0 because potential is constant. Differentiation of constant is 0. Now here at D, ED is equal to minus of dV. dV is here 4. Final is 0, right? Initial is 4. So 4 minus, here 4 minus 0, right? Isn't it? But the slope is negative, isn't it? Slope is negative. So here final minus initial, isn't it? Final minus initial, that is 0 minus 4, right? 0 minus 4 divided by 1. So ED is equal to 4 volt per meter, right? Now ED is greater than EB, okay. ED is greater than EB and EA equal to EC, right? EA equal to EC, correct, and EB is lesser than ED, correct. So the correct option is D. Okay. Next question, question number 12. Figure shows 3 points A, B and C in region of uniform electric field E vector, okay. The line AB is perpendicular to BC. Here the line AB is perpendicular to BC, is parallel to the field lines. Here BC is parallel to the field lines. This is the field lines, right? Then which of the following holds good? VA, VB and VC represent the electric potential at points A, B and C respectively. Okay. So this is VA at point A, VB at point B, VC at point C. Okay. At A and B, the potential is same, right? At A and B, potential is same because it's a equipotential surface. On equipotential surface, here the electric field is perpendicular to the surface, right? Here at every point, here, the electric potential is same, right? Isn't it? Electric potential is same. Same here. I am drawing here. I draw the 3D diagram, right, of this one. So VA equal to VB, VA equal to VB, and potential at C is lesser than potential at B, right? As you move in the direction of the electric field, potential decreases, right? So VB, VA equal to VB, which is greater than VC, right? Which is greater than VC, which is greater than VC. Okay, so the correct option is D. Next question, question number 13. A dipole of dipole moment P and moment of inertia I is placed in a uniform electric field E vector. If it is displaced slightly from its stable equilibrium position, the period of oscillation of dipole is. Okay, so this is the uniform electric field. Okay, dipole is placed in a uniform electric field. So this is 2D. Okay, positive charge and negative charge. Now it is slightly displaced. Okay, slightly displaced, plus Q charge and minus Q charge, right? Now it will start to oscillate, right? Because this is the direction of the force on plus Q charge and this is the direction of the force on minus Q charge. This is in stable equilibrium position. Now it is slightly displaced. Now it will start to oscillate. We need to find the time period of the oscillation, right? So what is the torque acting on this dipole? The torque acting on this dipole is minus PE cos theta. Why I am writing minus here? Because here I am considering the anti-clockwise torque, right? The clockwise torque. So torque tau equal to minus PE cos theta. And we also know that torque tau equal to I into alpha, which is equal to minus PE. Sorry, this is minus PE sin theta, not cos theta. Sorry, I'm really sorry. Minus PE sin theta. Okay, minus PE sin theta, not cos theta. Minus PE sin theta. Okay, torque tau equal to I into alpha, which is equal to minus PE sin theta. Minus PE sin theta, right? We know that alpha is equal to minus omega square into theta, right? Minus omega square into theta. Here for small value or small angle, sin theta is equal to theta, right? So I into minus omega square theta equal to minus PE theta, right? Theta will get cancelled. So solve this. Omega is 2 pi by t. Now solve this, you will get time period t equal to 2 pi into root of I divided by PE. Okay, 2 pi into root of I by PE. So the correct option is D. Okay, next question, question number 14. The difference between the equivalent capacitances of two identical capacitors connected in parallel to that in series is 6 microfarad. The value of capacitance of each capacitor is. Okay, so the difference between equivalent capacitances of two identical capacitors connected in parallel to that in series, right? So that is here when two capacitors are connected in series, right? Equivalent capacitance is C by 2, right? 1 by C1 plus 1 by C2, right? So that is 1 by C plus 1 by C, that is 2 by C. So C net equal to C by 2. And when it is in parallel, equivalent capacitance is 2C, right? Okay. Now the difference between these two capacitances, 2C minus C by 2, which is equal to 6 microfarad, right? Now this is 2 into 2, 4, 4 minus 1 is 3. So 3C by 2 is equal to 6 microfarad, 6 microfarad, right? So 3 2s are 6. So C equal to 4 microfarad. So capacitance of each capacitor is 4 microfarad. So option A is the correct answer. Okay. Next question, question number 15. Two metal plates are separated by 2 centimeter. The potential of the plates are minus 10 volt and plus 30 volt. The electric field between the two plates is. Okay. So electric field between the two plates E equal to here minus dV divided by dx, right? E equal to, So what is the value of minus dV by dx? Here minus dV, that is potential difference, right? Here the potential difference is minus of, potential difference will be 40, right? 30 minus of minus 10, 40, right? Sorry, minus 10 minus 30, okay? Minus 10 minus 30, potential difference is minus 10 minus 30 divided by dx. Dx is 2 centimeter, that is 2 into 10 to the power minus 2. So E equal to plus 40 divided by 2 into 10 to the power minus 2, right? So 2 20s are 40. So 20 into 10 to the power 2, that is 2000. So E equal to 2000 volt per meter. Okay. So the correct option is A. Next question, question number 16. The equivalent capacitance between A and B is, okay, we need to find equivalent capacitance between A and B. Simple one, right? So here 200 picofarad, 200 picofarad, both are in series, right? So now here the capacitance of these two will be 50 microfarad, sorry, 50 picofarad, right? So 1 by 100 plus 1 by 100, that is 50, 1 divided by 50. So equivalent will be 50 picofarad, okay? So now here this 50 picofarad is in parallel with this 50 picofarad, right? So C1 is equal to 50 plus 50, that is 100 picofarad, right? Now it is in series with 50 picofarad, right? C2 equal to 50 picofarad. Now 1 divided by C net is equal to 1 divided by C1, that is 1 by 100 picofarad plus 1 divided by 50, okay? Take 1 by 50 as common. So 1 divided by C net is equal to 1 plus 1 by 2. 1 plus 1 by 2 is 3 by 2. So 1 divided by C net is equal to 3 divided by 100. So C net is equal to 100 divided by 3 picofarad. So the correct option is D. Okay. Question number 17. A capacitor of capacitance C charged by an amount Q is connected in parallel with an uncharged capacitor of capacitance 2C. The final charge on the capacitor is here. This is the capacitor C, okay? It is charged by an amount of charge, amount of Q, okay? Amount Q. Then it is connected to the another capacitor 2C, okay, with parallel, in parallel, okay? So it is uncharged capacitor, this one is charged capacitor. The final charge on the capacitors will be, when you connect the capacitor, the charged capacitor to the uncharged capacitor 2C in parallel, what happens? There will be a charge distribution, right? Until the capacitance of C, sorry, until the potential of C equals to potential of 2C, isn't it? Now the common potential V C equal to the total charge is Q divided by C equivalent. C equivalent is C plus 2C, that is 3C, right? So this is the common potential. Now let us find the charge on C and 2C, right? The charge on C is Q1, okay, which is equal to the capacitance of the capacitor C into common potential Vc. Now Q1 is equal to, solve this, you will get Q divided by 3, okay. Next Q2 is equal to here 2C into Vc, right? Q2 equal to here 2C into Vc is Q divided by 3C. So C will get cancelled. The charge on the second capacitor, that is capacitance 2C, is equal to 2Q by 3. So the correct option is A, okay, Q by 3 and 2Q by 3. Next question, question number 18. A particle of mass m and charge q is placed at rest in uniform electric field E and then released. The kinetic energy attained by the particle after moving a distance y is. Okay, so here this is the particle, mass of the particle is m, the charge is q, okay. So it is placed in a uniform electric field E, okay. initially it was at rest, okay, now it is released. Because of the electric field, the charged particle will start to move, right? So we need to find the kinetic energy of this particle, okay, kinetic energy of the particle when the particle moves distance y, okay. So let us find the velocity of the particle when the particle moves at distance y, okay. Now apply third equation of motion. Third equation of motion is v square equal to u square plus 2as, okay. U is 0, right? So v square equal to 2 into a into s. Here kinetic energy is mv square by 2, right? Mv square by 2. A is acceleration, right? Isn't it? We need to find the acceleration of the charged particle when it travels distance y, okay. That is at this point. The distance is y. Now here the charged particle experiences force, right? Isn't it? The force F equal to m into a, right? F is m into a. So acceleration A equal to F divided by m. So in this case, the force is electrostatic force, right? So electrostatic force is Q into E divided by m, okay. A equal to Q into E by m. Now V square equal to here 2 into Q into E divided by m into S, okay. In this case S is y, okay, S is y. Now substitute V square to the kinetic energy equation, right? Now kinetic energy is equal to 2 QE by m V square, okay, into m, right? QE by m into y, okay. 2 QE by m into y into m divided by 2, right? So 2 will get cancelled, here m will get cancelled, right? Kinetic energy is equal to Q into E into y. So the correct option is A, okay. QE into y into Q into E into y, okay. Next question, question number 19. A system of two charges separated by a certain distance apart stores electrical potential energy. If the distance between them is increased, the potential energy of the system, option A, may increase or decrease. Okay, let's see. Here the system of two charges, okay, Q1 and Q2, okay, Q1 and Q2 separated by a certain distance, separated by a certain distance apart, okay. So it stores electrical potential energy. What is the equation of the electrical potential energy? Electrical potential energy U equal to K into Q1 into Q2 divided by D, right? If the distance between them is increased, right? Here D is increased. The potential energy of the system, okay, let's see whether it increases or decreases. If Q1 and Q2 are positively charged, that is like charges, Q1 into Q2 is greater than 0, right? So then the potential energy decreases, right? Isn't it? If Q1 and Q2 both are positive, then potential energy decreases, isn't it? As D increases, isn't it? Or electrical potential energy stored decreases as the separation increases, isn't it? If Q1 and Q2 are unlike charges, that is Q1 is either Q1 is negative or Q2 is negative, okay. Either Q1 is positive, Q2 is negative. Either Q1 is negative, sorry, either Q1 is positive, Q2 is negative, okay, or Q1 is negative, Q1 is positive, Q2 is negative. So which is lesser than 0, right? Now the potential energy is negative, right? Potential energy is negative. Now if you increase the value of D, that is the separation, potential energy will also be increases. Why? Because potential energy negative, right? So if you increase the value of D, potential energy will also be increases, okay, because of the negative. So the potential energy may increase or decrease, okay, it depends on the charge. So option A is the correct answer, okay. Yeah. Question number 20. A mass of 1 kg carrying charge of 2 coulomb is accelerated through a potential of 1 volt velocity acquired by it is, okay. So here the 1 kg mass, okay, and charge 2 coulomb accelerated through a potential difference of 1 volt, right? Accelerated through a potential difference of 1 volt. Now we need to find velocity acquired by the mass, right? Okay, so kinetic energy of the, now apply the conservation of energy theorem. Okay, conservation of energy theorem. So what is the potential here? What is the potential energy? Okay, so potential energy is equal to Q into V, right? So Q into V, electrical potential energy, which is equal to kinetic energy, right? Kinetic energy of the particle, right? Or kinetic energy gained by the particle, half m into v square. We need to find v square, right? Sorry, v, right? V equal to, okay, this is small v. Okay, so small v, that is velocity, is equal to root of 2m. So here this will be root of 2 divided by, here 2 divided by m into q into v, right? So 2qv divided by m. Now v is equal to root of 2 into q, 2 into here the potential is 1, right? Divided by m is 1. So v equal to 4, right? Root of 4. Root of 4 is 2, right? 2 meter per second. So the correct option is B. Okay. Yeah. Next question. Question number 21. For the arrangement of a capacitor as shown in the circuit, so this is the given circuit, right? The effective capacitance between A and B. Between the points A and B, the capacitance of each capacitor is 4 microfarad. Okay, so we need to find the effective capacitance between A and B. So now look at closely. Oh, okay. So now observe carefully. So the given circuit is the balanced Wheatstone bridge, right? I can redraw the circuit diagram. So this is how it looks like. Point A, right? And then point B. Okay. So 4, 4, 4, 4 microfarad, right? Microfarad. Isn't it? Right? So this is the, okay, let's name each points. Okay. So this is A. Now B, sorry, this will be C. Okay. C and D, right? So in this case, this point is C, right? Here in this diagram, this point is C, this point is D, right? So this middle 4 microfarad is this one, right? So this is the balanced Wheatstone bridge. How? Take the ratio 4 microcoulomb, sorry, more 4 microfarad by 4 microfarad 1, 4 microfarad by 4 microfarad 1, right? So both sides the ratio is same, right? So this is balanced Wheatstone bridge. So we can neglect this capacitor, right? Now I can redraw this circuit diagram as 4 microfarad, 4 microfarad, and then again 4 microfarad, 4 microfarad, right? Isn't it? So this is point B. Okay, let's say this is C1, C2, here this is C3 and C4. Okay, C1, C2, C3, C4 is equal to 4 microfarad. So now solve this. These two are in series, right? So C1, C2 divided by C1 plus C2, right? Plus these two are in series, right? And then these two are in parallel. So C1, sorry, C3, C4 divided by C3 plus C4. Then you have to add it, right? So this is net capacitance between A and B. Now the net capacitance between A and B is equal to, here C1 into C2 by C1 plus C2, that is 4 into 4 by 4 plus 4, right? That is 2 microfarad, right? 2 microfarad plus same thing, 2 microfarad. Solve this, you will get 4 microfarad. So the correct option is A. Okay. Next question, question number 22. The work done to move a charge on an equipotential surface is, the direct question, right? It is 0. right? So this is the surface, okay, equipotential surface. At every point the potential is same, right? Potential is same. Work done is equal to q into change in potential, right? Or potential difference. Potential difference is 0, right? Potential difference is 0, so work done will also be 0. On equipotential surface potential difference is 0, right? Any 2 points, between any 2 points, so work done is equal to 0. So correct option is D. Okay, next question, question number 23. Two capacitors of 3 microfarad and 6 microfarad are connected in series and potential difference of 900 volt is applied across the combination. Okay, so this is 3 microfarad and 6 microfarad connected to a potential difference or the potential 900 volt, right? These two are connected in series. They are then disconnected and connected in parallel. Okay, so they are then disconnected and connected in parallel, right? The potential difference across the combination is, so we need to find potential difference across the combination. So anyway, this is in parallel, right? Isn't it? So potential difference across 3 microfarad is same as potential difference across 6 microfarad. That is, we need to find the common potential, right? Okay, so how to find the common potential? Here the common potential Vc equal to total charge divided by net capacitance, right? Or C equivalent, right? So let us find the total charge, right? So these two are connected in series with 900 volt, right? So in series the charge remains same, right? The charge does not change, charge remains same, isn't it? That is, charge on 3 microfarad is same as charge on 6 microfarad, right? So let us find charge on 3 microfarad and 6 microfarad, that is, both are same, right? So these two are in series. Take the net capacitance. What is the net capacitance? 1 by 3 plus 1 by 6, that is 1 by 2, right? So the net capacitance of this series combination is 1 by 2, right? So 1 by 2, 1 by C net is equal to 1 by 2, right? That is 2 microfarad. Net capacitance of these two series combination is 2 microfarad, right? C net dash, okay, 2 microfarad. So now it is connected with 900 volt battery, right? So let us find the charge. The charge Q is equal to C net dash into V. Now the charge on each capacitor will be C net dash is 2 microfarad and V is 900 volt. This will be 1800 microcoulomb, right? 1800 microcoulomb. So now we can easily find the potential difference across 3 microfarad and 6 microfarad, or potential difference across the combination, right? So potential difference across the combination Vc is equal to, here Q is 1800 microcoulomb, okay, divided by C net. C net is here equivalent capacitance of this parallel combination, that is 9 microfarad. So micro will get cancelled. So Vc is equal to 200 volt. So potential difference across the combination is 200 volts. So the correct option is C. Okay. Next question. Question number 24. A system of two capacitors of capacitance 2 microfarad, 4 microfarad, okay, microfarad, connected in series across a potential difference of 6 volt. The electric energy stored in the system are, okay, so here 2 microfarad and 4 microfarad connected in series across a potential difference 6 volt, okay, 2 microfarad and 4 microfarad. The electric charge and energy stored in the system, right? Okay, so these two are in series, right? So the charge on 2 microfarad is same as 4 microfarad, right? So now take the net capacitance or equivalent capacitance of this series combination. What is the equivalent capacitance? Here 1 divided by C equivalent is equal to 1 by 2 plus 1 by 4. So 1 by C equivalent is equal to, here this will be 1 by 2 C, 1 by 2 microfarad plus 1 by 4 microfarad. 1 by 2 microfarad plus 1 by 4 microfarad. 1 by 2 is 0.5, 1 by 4 is 0.25, 0.5 plus 0.25, that is 0.75. 0.75 in fraction is 3 by 4, right? So 3 divided by 4. C equivalent is equal to 4 by 3 microfarad, right? 4 by 3 microfarad. This is the C equivalent, right? So let us find the charge on each capacitor, right? Let us find the charge on this C equivalent. Okay. Now the charge Q equal to C equivalent into V. Now Q equal to C equivalent. So that is 4 by 3 into 6, right? So this will be 2. So Q is equal to 8 microcoulomb, right? So the charge on each capacitor is 8 microcoulomb, isn't it? So what we need to find? Okay, we need to find the charge on the electrical charge and energy stored in the system, right? So this is the electrical charge stored in the system, isn't it? So let us find the energy stored in the system. Energy stored in the system, U equal to half into here Q into V, right? Half into Q into V. So U equal to half into Q is 8 microcoulomb into V is 6. So this will be 4, 6 4s are 24. So 24 microjoule. This is the energy stored in the system. This is the charge stored in the system. So the correct option is B. Okay. Next question. Question number 25. 2-point charges A equal to 3 nanocoulomb and B equal to 1 nanocoulomb are placed 5 centimeter apart in air. Okay. So this is 3 nanocoulomb. Okay. Point charge A, and this is 1 nanocoulomb. Point charge B are separated by distance 5 centimeter apart. Okay. In air. The work done to move charge B towards A by 1 centimeter. Okay, so work done to move a charge B towards A by 1 centimeter is W, which is equal to charge of the point charge B into potential difference, that is final potential. Okay, final potential VF. Okay, VF. Yeah. VF minus VI. Okay, VF minus VI. Let us find the potential difference. Okay, so what is the final potential? Final potential is at this point, right? So let's say this is point P. Here this will be point X. Okay, so what is the difference between point P and X? 1 centimeter, isn't it? That is the charge 1 nanocoulomb moved towards A by 1 centimeter, isn't it? So now W is equal to QB into final potential is potential at X, that is K into QA, potential at X due to A. Okay, K into QA divided by R1 minus K into QA divided by R2. Okay, now W is equal to, here take KQA as common. Okay, so K into QA into QB into 1 by R1 minus 1 divided by R2. Now substitute the values. Here K is 9 into 10 to the power 9. QA is 3 into 10 to the power 9. QB 10 to the power minus 9. Okay, 3 into 10 to the power minus 9. QB is 10 to the power minus 9 into 1 by R1 minus 1 by R2, that is 1 by 4 minus 1 by 5. It's in centimeter, right? So this will be into 10 to the power 2. Now solve this, you will get W equal to 1.35 into 10 to the power minus 7 joule. So the correct option is B. Okay. Next question. Question number 26. The minimum value of effective capacitance that can be obtained by combining 3 capacitors of capacitances 1 picofarad, 2 picofarad and 4 picofarad is. We know that if we connect the capacitors in series, we will get the minimum values. Okay, if we connect the capacitors in parallel, we will get the maximum values, isn't it? The effective capacitance increases. If we connect the capacitors in series, effective capacitance decreases, right? So 3 capacitors of capacitances, 1 picofarad, 2 picofarad, 4 picofarad. Okay, these two are connected in series, right? Now, okay, now the effective capacitance, that will be 1 divided by 1 plus 1 divided by 2 plus 1 divided by 4. This is 1 divided by C effective. Okay, now 1 divided by C effective is equal to 1 plus 1 by 2 plus 1 by 4, that is 3 by 4, right? So 3 by 4. Now C effective is equal to 4 divided by 7 picofarad. So the correct option is B. Next question, question number 27. Two capacitors of 10 picofarad, 20 picofarad are connected to a battery to 200 volt and 100 volt sources respectively. If they are connected by the wire, what is the common potential? Okay, here two capacitors, 100 picofarad and 20, say they didn't say it's a parallel plate capacitor. Okay, it can be any capacitor. Okay, it can be any capacitor. So 10 picofarad and another capacitor 20 picofarad are connected to a battery of 200 volt and 100 volt sources, okay, respectively. If they connected by the wire, what is the common potential of the wire, right? So here we need to find common potential, right? So what is the charge on 10 picofarad? The charge on 10 picofarad is here 10 C into V, right? 10 into V. V is here 200, right? Q equal to 10 into 200, that is 2000. 2000 picocoulomb or 2 nanocoulomb. Okay, 2 nanocoulomb. Similarly, the charge on 20 picofarad is same thing, 20 into 100, right? So that will be 2000. So 2 nanocoulomb, right? Now we need to find the common potential. The common potential VC is equal to the total charge or net charge divided by net capacitance, right? Total charge divided by net capacitance, isn't it? So VC is equal to total charge is 2 plus 2, 4 nanocoulomb, right? Divided by C net. C net is 20 plus 10. 20 plus 10 is 30, right? 30 picofarad, right? 30 into 10 to the power minus 12. Here nano is 10 to the power minus 9, right? 10 to the power minus 9. Now here this will be 4 divided by 30, right? Isn't it? So 10 will get cancelled. 4 by 3 is 1.333, right? Isn't it? 4 divided by 3, sorry, 4 divided by 3 is 1.333. So this is 10 to the power minus 11. So 10 to the power minus 9 by 10 to the power minus 11 is 10 to the power 2, right? So this will be equal to 133.3 volt. So the correct option is B. Okay. Next question, question number 28. A particle of mass 1 gram and charge 1 microcoulomb is held at rest on a frictionless horizontal surface at a distance 1 meter from the fixed charge 2 millicoulomb. Here 2 millicoulomb is a fixed charge, okay, and 1 microcoulomb, particle of mass 1 gram, 1 microcoulomb okay, is rest on a horizontal surface, right? And the separation between, initial separation between these two charges is 1 meter, okay. If the particle is released, it will be repelled. The speed of the particle when it is at a distance 10 meter from the fixed charge, okay, when you release this, it will start to move. This 1 microcoulomb charge will start to move towards right, isn't it? That is, it will repel, right? So we need to find the speed of the particle when it is at a distance of 10 meter from the fixed charge, okay, 10 meter from the fixed charge, that is 2 millicoulomb, 10 meter, right? So at this point we need to find the velocity v. Apply conservation of charge. There is no external force acting on our system, right? Apply conservation of charge. Here, according to conservation of charge, initial total energy is equal to final total energy, right? Now initial total energy, that is potential energy plus kinetic energy, right? So potential energy is K into, so this is Q1 and Q2, okay, K into Q1 into Q2 divided by R, right? R equal to 1 meter, plus kinetic energy is 0. Next, kinetic energy of the particle when it reaches at this point, that is the distance between 2 millicoulomb and 1 microcoulomb is 10 meter, okay. So half m into v square plus the potential energy at this point, that is K into Q1 Q2 divided by R dash, okay. Now here half mv square is equal to, take K Q1 Q2 as common, so this will be 1 by R minus 1 by R dash, okay. So now V is equal to root of 2 divided by M, right? That is 2 into K Q1 Q2 divided by M into 1 by R minus 1 divided by R dash. So now solve this, okay. So V equal to root of 2 into Q1, Q1 is 1 microcoulomb, right? That is 10 to the power minus 6, 2 millicoulomb, 2 into 10 to the power 3 minus 3 divided by M is 1 gram, that is 10 to the power minus 3 kg, into K is there. The value of K is here, the value of, what is the value of K? The value of K is 9 into 10 to the power 9, then 1 by R minus 1 by R dash, that is 1 minus 1 by 10, okay. 1 minus 1 by 10 is 9 by 10, okay. I am writing here, it's bit, okay. So K into 9 by 10. So K is 9 into 10 to the power 9, okay, the value of K, okay. So then here, if you solve this, you will get 180 meter per second, okay. Speed V equal to 180 meter per second. Solve this, okay, you will get this answer, V equal to 180 meter per second. Next question, question number 29. 4 metal plates are arranged as shown. Capacitance between X and Y. A, area of each plate. D, distance between the plates. Okay, I will redraw this diagram. Okay. Okay, you can solve this question in two ways. Okay. So one, draw circuit diagram, and another solving the capacitance in conventional way, that is first give charge and then find electric field between the plates, right, and then potential and then Q by V, right. Okay, so the first one, I can redraw this diagram. Here this is X, right, X connected to the plate 1, right, 1 is in front of 2, right, then 2 is connected to 4, right, 4 is in front of 3, 3 connected to Y, and then 2 is in front of 3, right, here 2 is in front of, sorry, 4 is in front of 3. 4 is in front of 3. Now 3 is connected to Y here, right? Now these two are in series, sorry, these two are in parallel, right? Then it is in series with this one, right? C, 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 right? Identical capacitors. Why? Because area is same, distance between them is also same, right? Okay, so now these two are in parallel, right? That is 2C. Then it is in series with C. So C net is equal to C into 2C divided by 3C, C1 plus C2, that is C plus 2C. So C net is equal to 2C by 3, right? So what is C? C equal to epsilon naught A divided by D. Now C net is equal to 2A epsilon naught divided by D. So this is one way, right? And another way, here draw the circuit diagram. Here this is X, right? Plate X, isn't it? Sorry, this is plate 1 connected to X, and here this is Y, plate 3. 1, 2, 3, 4. 4 and 3, sorry, 2 and 4 are connected, right? Now give charge, that is give charge to X and Y. So this is Q and minus Q, that is I am connecting X and Y to a battery. Okay, charge on X is Q and charge on Y is minus Q. Why? Y is connected to the negative terminal, X is connected to the positive terminal, right? So then find the electric field. So before that we need to find charge on each side of the plate, right? So at this side here the charge will be Q1 plus Q2 divided by 2, right? On outer surface, right? Or this surface here and here, Q1 plus Q2 by 2. Q1 plus Q2 by 2 is Q only, right? Q1 plus Q2 by 2. Here this will be 0, right? Q is here Q is Q1 is Q, Q2 is minus Q, so this will be 0, right? It will be 0. So then the charge on the inner surface is Q. We know that the opposite faces has the magnitude of the same charge but opposite sign, right? So minus Q, right? Then charge on this side is X, okay? So this will be minus X, right? And this will be minus Q plus X, okay? And here Q minus X, right? Q minus X, here this will be 0, right? So then find the charge on each surface or the value of charge. Here the potential difference is same, right? Delta V and delta V, because these two are connected, right? Second plate and fourth plate are connected, so potential difference will be same, right? So now find the potential difference. Potential difference is electric field into D. Electric field will be here minus into E into D, right? So this will be minus of minus X divided by A epsilon naught into D, potential electric field between these two plates, okay, into D is potential difference, which is equal to here minus of minus Q plus X divided by A epsilon naught into D, okay, A epsilon naught into D. Now D divided by A epsilon naught, D divided by A epsilon naught will get cancelled. X equal to Q by 2, X equal to Q by 2, here minus Q by 2, right? So this will be minus Q by 2 and Q by 2, right? So now find the electric field, right? So electric field between these two plates, that will be Q divided by A epsilon naught. Here this will be Q divided by 2A epsilon naught. Now what is the potential difference or potential between this one, X and Y? So that will be V, which is equal to here 3Q divided by 2A epsilon naught, right? Potential is Q divided by A epsilon naught into D. Here Q divided by 2A epsilon naught into D. The distance between each plate is same, right? So 3Q divided by 2A epsilon naught into D. Then C equal to Q by V, right? C equal to Q by V. So you will get the answer C equal to 2a epsilon naught divided by 3 into D. Okay, so the correct option is C. You can solve this question in two ways, right? Yeah. 30. A parallel plate capacitor is charged and then isolated. The effect of increasing the plate separation on charge, potential and capacitance respectively. Okay, so this is the capacitor. It is charged by the amount Q, right? By applying the potential difference V, isn't it? V. Okay, so now this capacitor is disconnected. Initially, it is connected to the battery V, battery EMF of the cell V. Okay, now it is disconnected. Okay, charge on the capacitor is Q and capacitance is C. Okay, disconnected and isolated, right? Now the plate separation here, by increasing the plate separation, what happens to the charge, potential and capacitance, right? So if you increase the separation between the plates, the charge remains same, right? It is disconnected from the battery and isolated, right? So we know that in an isolated system, the net charge remains same, right, or constant, right? So the charge remains same or Q equal to constant. The charge is constant, right? So now you have increased the distance or separation between these two plates, right? So now what about the potential, right? So potential V equal to E into D. If you increase the value of D, potential will also be increases, right? Potential will also be increases, isn't it? So potential increases. So let's see the capacitance. Capacitance of the parallel plate capacitor is here epsilon naught A divided by D. If you increase the value of D, capacitance decreases, right? So C decreases. So Q is constant, capacitance increase, C capacitance decreases. Okay, Q is constant, capacitance decreases and potential increases, right? So the correct option is D. Thank you so much. So if you love this video, please like and share. Okay, and if you want to watch more videos like this, please subscribe. Thank you.